So, welcome. My name is Blaine Whittle. I'm with Blizzard Entertainment, where I've been for 11 years. Currently, I'm a tools engineer on the Starcraft II team. My goal today is to show you a different way to do builds that can drastically reduce build times. I have a lot of ground to cover. I'm going to go through a lot of slides fairly quickly. These slides will be up online. I'm going to leave time for questions at the end. So this is what our game sizes have looked like over the years. Actually, a little side note, this Sunday will mark the 15th anniversary of the release of Starcraft I. So this actually doesn't reflect build sizes, as this is just game client, and as that it's just English. So it's not including server-side components or other locales. As content sizes grew, build times became problematic. So not only are Blizzard's development cycles a tad bit on the longer side, but we have a bad habit of patching and updating games long past release. In fact, we still make Warcraft 3 and Diablo 2 builds from time to time. So when it comes to build systems, we need a solution that can keep up with our growing data sizes and will scale to meet the needs for our next few years. When it comes to scaling, the obvious solution is to add more hardware. Unfortunately, it's not that simple. When it comes to scaling, the degree of scaling is critical. A number of build systems allow scaling by breaking work up and executing it on multiple machines. In fact, we had an in-house build system that already did this. But what we found is every time we added another server or two, we had to go in and refactor the build to break it into smaller and smaller steps. This process was both time-consuming and error-prone. So here's what the dependency graph looks like for a large-scale distributed system. Each dot in this graph represents a single task, and lines represent dependencies between the tasks. Ironically, this is actually a small build here. This is a dependency graph for a 4-minute code build, but it does kind of show the bottom-up bottom-up approach that we want. Ideally, we want a system where we can define the work to do, and then have the system figure out the best way to partition the workload and split up among the available hardware. I'm not saying the top-down approach is wrong. What I'm saying is that when it comes to scaling, 10 tasks is not enough. 100 tasks is not enough. 1,000 tasks is a good start. There are a number of benefits to going with this route. First, we can extend this dependencies between from just tasks to files. Now, one reason why build systems are typically I/O bound is we end up with a lot of wasted I/O. One example is fetching and syncing a large directory, which includes a whole lot of files that we actually don't need. So if each task is explicit about the files it depends on, we can avoid wasted I/O such as this. Now, the term lightweight here is relative, but ideally a task should only take a few seconds to complete. However, that's not always feasible. So not only do lightweight tasks enable scaling, but can improve stability as well. A simple default behavior of reattempting tasks that fail can often remove intermittent errors altogether that result from just random network or server issues. If you consider the other extreme, let's say we have a task that takes 30 minutes to run. You would never want the build server to automatically reattempt that. Like, you would want someone to figure out what's up and intervene, because it would just be too costly to reattempt. starting out, I thought our needs were rather simple. We want to scale our existing tools for Mac, Windows, and Linux. We build assets on and for each of these platforms. These tools are common everyday command line executables or scripts, and we want to be able to scale those tools over any number of platforms and machines. Now, starting out, I assumed someone else had solved this problem for us, and I just needed to find it. But when I went looking, I found that every tool or technology appeared to only meet two of these three goals. Once again, what we need is the ability to scale common command line tools to multiple machines on multiple platforms. So here I'm just restating the same requirements. We want to be able to scale normal command line tools. Not only do we want to scale existing tools, but we want to keep the same development model. Everything can be seen as some form of data transformation. Even compiling is just data transformation from source files to object code. The only thing these tools have in common is they read and write files. Now, to add a fourth requirement, we want something designed from the ground up to handle I/O. The best example I can think of is Google's MapReduce. It's an entire system designed for getting around I/O limitations. We need something similar, but can be applied to non-uniform data sets. So we set out to write our own build system, which named Sanity, to tackle this very problem. And so far it's been successful. Initially it was applied to WoW's build times. However, over the last year we've moved Starcraft II's builds to it and reduced build times from 8 hours to under 30 minutes, and that's without adding additional hardware. Now, Sanity was written in Erlang, and however, this talk is not about Erlang, but how to create faster builds, the details of which can be implemented in any number of alternative languages. So first I'll kind of go through some theory and abstraction, and then walk through a simple build to show how the different primitives fit together, and then talk about implementation details. So if you stop and think about it, the file system is really just an interface or API for operating system processes. If you can enforce immutability on files and then do some graph analysis, you have a data flow pattern. Sanity was written in a functional language, but also has a very functional design. So the reason why we have immutable files is it simplifies graph analysis. It removes any ambiguity as far as file paths go. If files weren't immutable, we need a way to declare which version of a particular file path we were interested in. But if you think about it, making files in a build process isn't that big of a leap, since builds themselves are generally considered immutable. When I refer to build number 293, I'm referring to a specific set of unchangeable files. So one problem, if we want to scale existing tools, some tools do modify files. But really all we need to do is hide that fact by doing a copy on write. So we can copy the file to a different path and then modify that one. So one common example would be a signing task. So in this case, I'm signing foo.exe, and so one easy solution is just to rename one of the files. We basically have an unlimited file namespace to select from. A task is really any amount of work that reads and writes files, but it is the smallest unit of schedulable work in the system. So this is a little bit of terminology here. So I'm going to be showing a number of graphs, and the reason is that each build is nothing but a dependency graph. But what may not be obvious is that a key part of the system is that our build graphs change during execution. Dependency graphs are dynamic, but with restrictions to enforce our data flow pattern. primitive that enables graph mutation is the metatask. Metatask can do anything that normal tasks can do. However, they have the additional ability to create new tasks. So obvious question would be, well, why have that distinction? Why not just allow all tasks to create tasks? Well, it allows us to reason about the remaining work. Unevaluated metatasks are treated as an unknown, which means if we don't have any metatasks left in our queue, we know our graph is complete and will no longer change. And I'll walk through an example in a bit. Just trying to find my mouse here. There it is. Whoa. So I'm not going to, where are we? Okay, rules. So I'm not going to dive into rules too much, but it's very similar to make-style rules. So there's a glob syntax for generating tasks based on file name matching. So one interesting thing is map rules are evaluated anytime new tasks are created. However, reduce rules are only evaluated when the final metatask completes. So implementing a new task, Zanny, is really simple. Two functions are needed. So the first one describes the work to be done, and the second actually performs it. Okay, so I'm parse here. So the primary purpose of parse is to bind task lines to specific files. Parse can be seen as a contract as far as output files go. If a task declares it will create a file, it must, or it will result in error. The only exception to this is metatasks, where metatasks can optionally delegate the creation of files to new tasks that it creates. So parse may only use data from the task line when determining the task's input and output files. This means parse can't open or read any files directly. So in this, you also don't declare dependencies between tasks, just between tasks and files. As we can see easily in this, task foo creates file C, and we know that task bar requires file C, which means that task bar is dependent on task foo. So I showed this graph earlier. So if you visualize the same graph with file dependencies, you get this. So the point here is the previous graph can be generated from this one. Mention that parse function can't read or write files, which seems really restrictive. Often we have to look at the contents of a file just to determine what our other files are. So with this restriction on parse, what do? Well, it depends. If we're talking about output files and we need to inspect a file to figure out what our output files are, we can just implement it as a metatask. Metatasks are allowed to create files without defining them first. And that's okay. Metatasks are treated as an unknown. Now, however, if we need dynamic input files, there's a mechanism in place to handle this. So a parse function may optionally return a series of functions for mapping the contents of a file to additional input files. We only need to declare that the content of our input file is special and then provide a function for making sense of the file contents. The system will actually fetch the input files, read the data, and call our functions as needed. So to walk through an example, let's say we declare compile tasks whose parse function returns a single input file, in this case file.cpp. Now, in order to compile, we'll likely need any number of additional header files, which can be figured out by inspecting the contents of file.cpp. So our parse function will declare that file CPP is special and needs to be inspected in order to determine what the additional file dependencies are. So saying it takes file CPP, calls our closure function, and in this case returns file.h. So this process is recursive, in which case we inspect file.h to find out about 2 more header files, and the process continues. So both foo and include here will need to be inspected. It's worth noting that cyclic file dependencies are fine. It's cyclic task dependencies that we need to prevent. Now, while I've used C++ code files here as an example, the system can be used in many places where content files refer to other content files. Game asset files often refer to other asset files. So our second function is execute, which is where the actual work is performed. So prior to execute running, Sandy will set up our what we declared as our input files into our working directory. So more often than not, a task's execute function will just call out to a specific command line tool or script, in which case execute is a function that just maps data from a task line to command line parameters. So to illustrate how these primitives fit together, I'll step through a simple Visual Studio code build. The tool being compiled is this little GUEE app on the right called IcePack. IcePack is used for inspecting game archives. I've chosen it here because of its size. The entire build is only 29 steps. Same was created for data builds. However, I'm using a code build here as an example, as compiling and linking are commonly understood processes. So SANI was designed to scale common command line tools, which compiling and linking are. So just try to imagine this framework being applied to any other types of data transformation. First thing is evaluated is .sanity project file. This project file doesn't define any rules, just a single static task. So this is the first example of what a task line looks like. Task line is nothing more than an Erlang tuple. If you aren't familiar with the syntax, just think of it as JSON, but we can embed anonymous functions. Near at the bottom, we are mapping the trunk subversion repo to the build's root directory. Normally in a build system, this would end up as a full checkout of the entire repository. We can get away with it here due to lazy file fetching, which will be covered in a bit. So we start with our initial task line here, which is a VS solution, which is a meta task. So we call parse on it and learn that this has a single input file, which is a solution file. So if we look at our dependency graph, this is what it looks like. Solution task isn't connected to our target, however, it's a meta task, and meta tasks are always evaluated. Tasks might be pruned from the graph if determined to be unnecessary, but not meta tasks. So next step is executing our task, as it's the only one in the queue. So task execute step parses the solution file and emits additional task lines. These new tasks correspond to 2 Visual Studio projects referenced in the solution file. Both of these tasks are meta tasks themselves. So we repeat the process. So like before, we call parse on our new task lines. So here, this task line declares is dependent on the project file and will create an executable. Our other one here will create a lib file. So this is what our dependency graph looks like now. So we still haven't executed either of the Visual Studio Project tasks. So when we do, these metatask nodes will be expanded to include the newly discovered work. What to watch for is how our graph changes over time. So now we have 2 metatasks in our queue. So I'm only going to show the results of one of them, because otherwise this would be ridiculous. So if you notice, so this is a compile task. So if you notice, our task line has a bit more data than the previous ones. So task lines are opaque data structures. Only a task's parse and execute functions know how to make sense of a given task line. So all the data you see on a task line here will end up getting passed on the command line to our compiler during the task's execute step. So if you remember, tasks can only pass data to other tasks via task lines or output or with files. So, and like before, so we now have a bunch of new tasks we have to call parse. In this case, it is dependent on a C file and will output an object file. So rather straightforward. So and this is repeated. So this is the result of our graph after the first project file completes, and then after the second one. So at this point, all the metatasks are complete, yet we haven't done any actual work. But we are, we do know what every file that will be created at this point. So this is after the first compile task executes. So Sandy is recursively parsing and pulling in different header files. So this is after 2 more compile steps. So you can see this can get really large. So I'm just going to focus on this part for the rest of this little walkthrough. So this is after 4th compile. And skipping ahead some more. So finally, everything but our linker is done. So since the linker's dependencies are done, the linker can then run. So at which point our build is complete. So one thing is, if you look closely at this graph, our code is really a map-reduce pattern. So with compile being a map and linking being reduce. So I've displayed a number of dependency graphs because it's really the core of any build. However, there are a number of optimization patterns I wish I could had the time to cover. However, I've noticed that just simply treating each build as a graph and stepping back and looking at it, like most optimizations, seem obvious and natural. So I've walked through and shown how a small set of primitives can be used in a code compile. The nice thing about these primitives is they can be used to create very large and complex projects. This framework has been surprisingly flexible. We've used it to scale some very different types of projects. So all the use cases listed here were implemented with command line tools, none of which were written for cluster scaling. And moving the work to Sandy was something that was done after the fact. So here's the dependency graph for path map generation. So this is only part of a larger data build. This is the same build as the previous one, but includes file dependencies. So the green lines are file-to-file dependencies or game assets that refer to other game assets. So we've had builds that depend on over 1 million files, so these graphs can get quite large. Despite these massive data sets, we can still kick out a full build in minutes. So this is a dependency graph for generating Starcraft II shaders. Each green dot is a model file that's stored in Perforce. Each model in the game requires multiple shaders. So at one point, Starcraft II build had to generate half a million shaders. So prior to Sanity, this took an hour to generate. So now it takes 14 minutes to run. Additionally, we can now do incremental builds, which only take a few seconds. So before getting to implementation, there are a number of things we learned along the way. So we have a number of build graphs with, that have been upwards of 2.5 million edges. And we've kept this all in memory, which can get rather expensive. So in fact, prior to the 64-bit version of Erlang, we kept running out of memory. Overall, Erlang has been a good fit for this problem, but all languages and platforms have their warts, and Erlang is no exception. In fact, on the string handling performance, like at one point I did a profile and found like 90% of the time was spent in lowercasing file names. So I switched that to C. Visual Studio integration was part of initial proof of concept. However, with Visual Studio 2010, Microsoft switched that all to MS Build. So, I mean, some of the custom code that we wrote for parsing solution project files was obsolete. Final testing and bug fixing was very time consuming. So we performed a number of validation tests. We were making builds with two systems. The issue is the system we were replacing could take 8 hours to run. So means just we were likely limited to doing 3 validation tests a day, most likely 1, because we didn't want to tie up the build servers during the day. So everything so far has just been the interface and how to partition builds into smaller pieces. So ideally, we want a system to handle and hide the details such as cluster management, caching, and task scheduling. So the rest of this talk will cover those details. So first off, we found the typical repository checkout step as problematic, so we got rid of it. To understand the repository scaling problem, try to exaggerate the scenario. So imagine the problems you would encounter if you tried a simultaneous checkout or update to 50 build machines. Or imagine the problems related to managing 50 active branches on a single build server. How many builds have failed because subversion was in some invalid state or build folder or file was never properly cleaned up. So Sanity has a non-traditional repository interface. There is no checkout step. It just fetches files as needed on a per-task basis prior to execution. We've created drivers for a number of repositories, including Subversion, Perforce, Git, and SMB. The repositories interface isn't much more than returning a list of files and fetching single files. Sanity and Git both have an internal content addressable cache. However, one difference between the two is that Git has a compressed data store. Files in Sanity's cache aren't compressed. This way, there's less work to do when moving files between the cache and the working directory. In fact, there isn't any work at all. We rely on hard links between the working directory and the cache. I think hard links are a vastly underused file system feature. They allow us to construct working directory trees with nothing more than file system metadata calls. When combined with the caching system, hard links give us zero-cost branching. Sure, repos have zero cost for creating the branch, but often a new repo branch translates to a full folder checkout on one or more build servers. Lastly, we have the ability to map multiple repositories into a build's file namespace. Earlier, I mapped the code build to a single Subversion repo, but often we rely on files from multiple locations. So files are only grabbed from a repository if, one, they are required, and two, they aren't in the cache. Each machine in a cluster maintains its own cache, and files are often pulled from the caches of other machines. Cache is content addressable, so given the MD5 of a file, we can quickly check and locate that file. So tasks read and write files to a working directory. Sometimes the working directory is shared with other tasks. Sometimes the task will be isolated and requires its own working directory. Let's skip over a few things here. So file immutability is enforced via file system access restrictions, which also prevents cache corruption. So this is important. Imagine a scenario where a task inadvertently modifies a file that's been hard linked to or from our cache. What you would end up with is a case where the MD5 of the file name in the cache doesn't match the contents. This is bad. Takeaway here that the entire working directory can be virtualized and created and destroyed as needed. Working directories only exist while the build is running. All the files are hard linked in the cache, so when we nuke the working directory, no data is actually lost. All we need is a database to map the real mappings of file names to their hashes. So this is really handy for debugging, as we can recreate the working directory for any task at any point in the build after the fact. So this can very quickly give us the minimal data set to run a particular step. And this is just really useful for figuring out what's up. It's like, here's the command line, and here's the environment to produce whatever filled that single step. So a sanity cluster includes a master and any number of workers. So this is what the different components look like in a running system. The first key process is the builder, which just keeps track of tasks that are either running or blocked by another task. It's very similar to a call stack. Builder just dispatches running tasks to the next component, which is the build queue. Build queue partitions and routes work to specific machines, as each machine maintains its own task queue. Think of the build queue simply as a router. It makes initial assignment of each task to a specific machine. The build queue doesn't try to balance any work. In fact, it does the complete opposite, as it groups tasks and assigns an entire group of tasks to specific machines. We're purposely not balancing the work between the machines here. We're trying to optimize for cache hit rates. Tasks created by the same meta task often depend on the same set or subset of files. If we can execute related tasks on the same machine and near the same point in time, we can get really good cache hit rates. We aren't just improving the cache hit rate of Sanity's cache, but the OS file system cache and IO hardware caches as well. If 5 tasks all read the same input file, it's optimal to run those 5 tasks on the same machine and at the same time. Task grouping is critical for cache performance. So we map task to machine based on a hash of the task line. This way a task gets routed to the same machine each time. Consistent hashing helps maximize cache locality when adding or removing a machine from the cluster. We don't want to map tasks directly to machines. If we did that, anytime we added or removed a new machine, it would result in a large number of keys getting remapped. The term consistent hashing is nothing more than mapping keys to an intermediate layer. So in this example, consistent hashing means if we add a machine, only two keys end up getting mapped to a new machine. So I mentioned before that each machine maintains its own queue of tasks. This is called the node queue. Since each machine has its own local queue, each machine can start on a new task without having to coordinate with another machine. This gives us lower latency task switching. The node queue manages the fourth component, which is the runner. Runners manage the setup, execution, and error handling of tasks. It also does all the post-execution work, which is hashing output files, applying ACL, hard linking files into our cache, and so on. So a runner's lifetime is limited to the execution of a single task. So what about load balancing? When it comes to I/O, any algorithm that scales has to find the right balance between cache affinity and load balancing. For instance, MapReduce offers a great solution to this problem by sending tasks to where the files are located. Unfortunately, that type of system only works when the data is uniform and there's a one-to-one mapping between data chunks and files. So unfortunately, that doesn't work for us, so a new solution is required. So when implementing Sandy Scheduler, took a strategy from the thread scheduling world. The idea is each thread has CPU affinity and maintains its own queue. When a thread runs out of work, it just steals work from another thread. As mentioned before, each machine has its own work queue. Work is first pulled from the local queue. Thread work stealing will take work. The thread work stealing will take work from other threads, and it can get away with that because each core is essentially the same. However, when it comes to a cluster, work stealing can incur the cost of copying files between machines. So we don't want the ability of any machine to steal work from any other machine. The solution we came up with is to arrange the cluster in a loop, and then prioritize work stealing to neighbors in that loop. So the organization of this loop is set up and managed by the build queue. So here's an illustration of work stealing. So a machine runs out of work, at which point it sends a request to its two neighbors. And then if a machine can't fulfill a still work request, it forwards that request along the loop. So if and when work is found, the results are sent directly to the requesting machine. When work stealing, Sandy will try to maintain the same task grouping. So usually entire groups of tasks will be stolen as a unit. However, if a complete group isn't available, then a group may be broken up and split between neighbors. So I showed this task graph before. This build ran on a cluster of 4 machines. So if we assign a different color to each task based on the machine that executed that task, you get this. So this is the end result of the combination of task hashing, routing, grouping, and work stealing. The nice thing about this solution is the mapping between tasks and machines will largely be consistent between builds, even in the face of network topology changes. So overall, this leads to good load balancing and good cache affinity. This combination of approaches is what I call soft cache affinity. We get sort of of locality for both tasks and files, since files are pulled to the machine that needs it. Machines prefer to do work close to them and will only take work away from machines on their side of the loop when there is nothing else to steal. This gives us the best of both worlds. Machines are mostly dedicated to a subset of tasks, but work is still load balanced as needed. And so let's say we have a task, call it task foo, that's hashed to machine C. The most likely location of both input and output files for task foo would be machine C, followed by machines B and D, and then A and E, and then finally the least likely location to find those files would be machine F. So this is what Starcraft II's data build times look like at different cluster sizes. Each machine here has 24 hyper-threaded cores, so 8 machines translates to 192 cores. The uncached scenario here is mostly academic, as the only time that ever occurs is setting up a brand new cluster. The equivalent would be if your build did a full checkout from scratch as part of the build. And in this case, per-first server has become our bottleneck for the uncached case, but that really isn't a problem because that never really occurs. So scaling graph is largely based on the details of the project and the tasks in that project. For instance, here's a scaling graph for SAR2 shaders, which has a higher CPU to I/O ratio compared to the Starcraft II data build. So actually, this last weekend, I did a build of up to 13 nodes, and this build times went down to 5 minutes. So everything covered so far, everything's really fast, and everything was great, and then this asshole on the right showed up. So one of the motivations I mentioned was for making this was multi-platform, but I haven't really mentioned any of the challenges related to it. So 2 hardware divisions really means 3 task divisions. So any number of machines may be equipped to run any number of tasks. So it's actually a many-to-many relationship. What we found is generally tasks have similar requirements to other tasks. So the first step is to group the tasks and assign them an ID. Here I'm assigning a color to each unique group. So blue represents a group of tasks 1 and 3. Yellow represents the group of tasks 5 and 6. In order for consistent hashing to work, we only need to define a sort function for machines. Now, a default approach might be to define an ordering based on alphabetical comparison of machine names. Turns out that's not the optimal solution, but we do need some type of consistent ordering. So with our work stealing solution, we want to avoid situations like this, where one of the 2 machines capable of executing red tasks aren't neighbors in the loop. A gap like this means machine A can't steal any red tasks until all the white and yellow tasks are complete. This leads to suboptimal load balancing. So the trick here is to define an ordering that minimizes gaps between task groups. So it's an NP hard problem. However, we often don't need need a perfect solution, just a good one. So the solution is just to order machines from the most constrained task groups to the least, which in this case means we first assign red and blue as those are the most constrained, followed by white. For all intents and purposes, yellow can be ignored because it would have no impact on our results. So one ordering that works would be BACD, in which case I'm just swapping locations of A and B. And so this way, the machines can easily load balance their work even across different platforms. So this is kind of ends my presentation on how to create multi-platform scalable build. Multi-platform scalable builds. So, and we have some time here for some questions. I'll be happy to take any questions, but please use any of the 3 mics.
Did you determine that antivirus was screwing you over like everybody else did?
Yeah. Sorry, come again.
Did you determine that antivirus was messing up your I/O speed?
No. Don't. I can't say we have antivirus running on our build servers. So.
So I might have just missed this, but I didn't quite catch the reason why you have the restriction that the parse function can't read files.
Well, there's a number of reasons, but the simplest is parse determines what files we should fetch, and since we're using lazy file fetching, there is no guarantee that those files are present. So. And the other reason is parse is designed to be very fast, so because it may be executed multiple times.
Gotcha. So you're just delaying the execution of that logic.
Yes.
Yeah. Okay.
Hey, Andre, Riot Games. 2 presumably interrelated questions. How did you instrument this? And given that, assuming the build tool is 100% correct, how do you debug problems with either specification or configuration?
I don't know how to answer that. Is instrumented as far as performance, debugging, logging.
Okay, so I screw up one of the task definitions, and it does something weird to my build graph that makes everything explode. How quickly can you get to a root cause?
Well, actually, fairly quickly. There's a website that this generates, and for any given task, it'll show you all the errors, and then you can easily navigate to any of the links in the graph, if that makes sense.
Presumably, there's a class of errors with a dependency system like this that all they do is blow up the dependency graph, but not actually cause any kind of compilation problems or that sort of thing.
Well, at some point, whatever you are expanding would have to be evaluated or executed. Mm-hmm. And I'm assuming that would have to result in error. And so as such, you could be able to find that and navigate up to the parent to find it.
Thank you.
Did you use this for local builds on developers' machines?
Traditionally, it hasn't been, but it can be. There actually is a feature that there's a little Perl script that evaluates the local machine and finds out what's different between a base version and a subversion, and then sends up those differences up to a server, and then the cluster will do your local build, and then send the results wherever. So
yeah, that's cool. Thanks.
How many developers worked on Sanity, and what was the total calendar time between concept and implementation or rollout of the first version?
I would probably say 4 man-years calendar time was split up with some different projects, but there was between 3 and 4 developers for over a couple years. So,
Thanks.
Okay. So in one of your slides, you mentioned that you could pull data from multiple repositories like Git or Perforce, whatever. Did you ever actually do this for any projects, and why?
Mm-hmm. Well, yeah. Like actually, I think every project we have has that. For example, Starcraft II builds pull from 2 different Subversion repositories and from Perforce, as ARDA assets are stored in Perforce, and data and configuration files are in 1 Subversion repository, and code is in a 3rd. So,
cool. Thank you.
So say that I'm a code-phobic artist and I'm adding a new asset to the build pipeline and it needs to have its own task. Do I have to create one of those .sanity files, or do you sort of work from templates, or is there some sort of editor for these, or do the artists just have to learn how to input the system?
Well, if I understand your question correctly, that can be all handled by rules, in which case a certain file in a certain location has a particular meaning, and then that is mapped to a task that would execute.
So I could just add my model textures, et cetera, to a certain folder, and that's all the only time. Okay, cool.
So you mentioned you explored a lot of the different options and found that none of them really fit your bill. Are you going to bring Sanity to the masses, or is this just something that you're keeping internal?
Not sure. Actually, we've discussed a bit internally about open sourcing it, because we're not in the business to make build systems. It was just a problem that ran into, but that would require a bit of time. So like that's still being discussed, but this talk, at least in covering the architecture about it, is a first step.
So it sounds awesome, so I would love to use it. The other question I had, sorry for taking up so much time, but you mentioned you validated the old build versus the new build when you were switching, and how did you do that? Like, what was kind of your criteria for?
Well, that it was bit for bit exactly the same.
Did you find a lot of problems with tools that have timestamps and other dumb stuff in their output?
Actually, no. I mean, there were a couple edge cases, but I mean, most our games kick out game archives, and so those were bit for bit exactly the same. Well, eventually got there. I mean.
Okay, thank you.
Hi. Are any teams at Blizzard using this for doing anything like continuous builds, regular testing, that sort of thing?
Is your team still doing that?
Yes. Although this thing is really made for giant data builds, and so the game teams have Blaine talks about Starcraft II pushing down to the servers, the textures and other things to get that built. It really was more of an approach of, hey, we have builds that are taking 4 to 20 hours. We'd like to take it.
So just so everyone else can hear that, what Sanity, the problem tackled is large data builds, and not necessarily continuous integration, but it has been used for that, yes.
Okay, thanks.
I think I might have missed one portion. It seems like, is there a static relationship between file locations and the rules applied?
Yes and no. I mean, because meta tasks can create files, and so there is a dynamic nature of it. And so, like, the rules have to constantly be evaluated anytime new tasks are defined, and because we have to then call parse and all those to find out what the output files will be.
Are those meta tasks stored in a database separately, or does that architecture have to be rebuilt every time?
Yeah, it's part of how a whole build evaluates. So, the build execution process. So there is a database that occurs in the cluster so it can look up things and resolve it, but it's not like an external SQL database or anything.
Thank you.
Hi, I got the impression that this is for remote builds, basically, and not for the individual developers or artists' builds when they're working on their stuff. Could you please clarify that?
Well, short of it is designed to do a whole lot of work as fast as possible. Okay, and so actually there are features in that for doing developer builds. However, traditionally, the feature hasn't been used as much as I thought it would be. So does that answer your question?
I think you confirmed that, if I understand it correctly, but I'm just considering if you then have a separate build process for developers and artists as they work on their machine, and that could then risk differing?
No, it's the same process. It's like they can use a script because they have to, their local edits have to be transferred to the cluster. I mean, that's the only difference.
Okay, so the work is done in the cluster and then downloaded again to their machine?
Yes.
Okay.
Hey there. I really like the system. I think it's a great setup. I'm wondering, so in addition to reducing file I/O times, did you look into trying to reduce process startup times for individual assets? So rather than booting up, like, let's say, the shader compiler for each individual shader, keep it alive and kind of just feed the data?
So no, it's there is no, I guess, concept of a continual running task. Like, any task has a start and stop and has very defined inputs and outputs. And so kind of process overhead like that needs to be considered in the shader generation example. Like, I didn't do a one-to-one mapping between models and shader files. I actually just grouped some models. So we still had like 3,000 shader gen tasks, but I can tweak the level of granularity very easily based on that overhead.
Cool. Thank you.
Hi, I have two questions. I think I may have just missed the first one, but how many machines do you allocate per project? And the second one is, how many people do you have supporting this system?
Well, I guess per project completely depends on the project. On the Starcraft II, like we had 4, and actually just last week we upped that to 9. What was the second question?
How many people do you have supporting this system?
Well, that's still also somewhat on a per team basis, but I think 2.
Questions were exactly her question. So to follow up on that, does that include like hardware maintenance of the machines, these 2 people?
Yes.
Okay, so everything from assisting people to make sure the build system is working at their desks, the way they expect it to work, all the way through keeping hardware running?
Yes.
Okay, thanks. That's impressive, by the way.
Any other questions? Oh, got another one here. And we've got 2 minutes left, so.
So sorry if I missed this, but how do you propagate changes in the tools themselves? Because it looked like each build server has to be kind of a clone.
Well, it's an excellent question, but here's the thing. Any task in its input files will actually declare the tools themselves. Okay, so those will end up in the graph. If you don't declare those input files, you will not get the files. Okay, so it generally takes a little bit more time to get a set up working system, but when you do, it's very scalable and you don't have any of these hidden dependencies. And so that also means a couple other things, like an incremental build. If you have just a single DOL changes, that will, in the graph, correctly propagate everything that could possibly touch.
So pretty much all tools are built from source during this build?
No, I would say it depends. Some tools are, the binaries will be checked in. Some tools are built from source. It depends.
All right, thank you.
Oh, okay. So sorry, we're done. One last thing is to fill out the surveys. Anyways, that's it. So thank you.